Hello everyone, how's it going? Hope it's going well for you. Right, this is a presentation about the normal distribution, okay? The normal distribution in statistics. So I'm going to talk you through what we mean by a normal distribution and how it's useful, okay? Now this is something I would really love to have a board, an electronic board behind me to just put on all the different displays, because there's a lot of diagrams that are needed in this. So just bear with me with some of the dodgy diagrams I might be doing. This actually took me ages to do, okay? I'm hoping you're liking it. Maybe I'll just insert some screenshots of diagrams just to help you along the way, okay? Now these are examples of what we call a discrete random variable, okay? A discrete random variable. I often abbreviate that to DRV, but this is for discrete data. And when you're doing discrete data, you normally draw a chart with bars and gaps in between them, okay? So just imagine these, it took me ages to draw these, all these bars nicely stacked next to each other, and you've got gaps in between them, okay? Here, I got a bit fed up and I just didn't draw the bars, I just drew the lines, okay? I'm hoping you're fine with that. Now it's important for you to recognise straight away the differences in skewness with these data, okay? So this data, for example, the one I'm highlighting most, is the one that's got a symmetrical distribution. I'm hoping you can understand why it's symmetrical. It's because if you look at the highest bar right in the middle, then alongside that you've got the next highest bar, and then either side the next highest bar, and so on. It's a very symmetrical and, let's just say, aesthetically pleasing look about that chart, okay? That's for symmetrical distribution. That's important because the normal distribution, which we'll look at soon, is for symmetrical data, okay? Let's just talk about what it looks when there's skew. So this is what a positive skew looks like, and this is what a negative skew looks like. Obviously, you might have seen these on histograms as well, okay? Now, in terms of what this might look like for an actual distribution, I'm going to show you a screenshot now of what it looks like when you're rolling two dice. So here's my screenshot, and you can see we're rolling two dice, and the most expected value, the expected value score is 7. That's why that bar is right in the middle. And then equally expected either side that is a total score of 6 or 8. And then next to that you've got a total score of 5 or 9 and so on. All the way to the ends, the expected probability of getting a 2 or a 12 is exactly the same. So when you're rolling dice, when you do the experiment a lot of times, when I say a lot, I'm talking about 1,000 or 10,000 or even more, then you'd expect this nice distribution to occur, okay? And it gives us an idea of the spread of results that we're getting. So that's a nice, a cleaner looking diagram than one I've drawn about rolling dice, okay? Right, back to my board now then. You see I've erased the diagrams I don't need, because I'm not talking about skew data in this unit. We're talking about symmetrical data, okay? So I'm just going to focus on that one. Let's just remind ourselves about what happens when we've got symmetrical data. You'd have seen this a few units back, but you need to have a reminder, okay? So when we've got symmetrical data, it's important to recognise that the mean, median and mode, they're all exactly the same. So when you do a calculation, the median, mode, mean, they're all the same, okay? So that's an important note. Now, you've also come across skew and symmetrical distributions when you looked at box plots. And this is what a box plot might look like. I've tried to draw it so it looks as symmetrical as possible. The important thing to look for here is that that gap should be the same as that gap there. Or, in terms of calculations, the difference between the median and the lower quartile, Q2 subtract Q1, will be the same as difference between the upper quartile and the median, Q3 subtract Q2, okay? So those are tests that we need to know. Now, in terms of an examination question, a simple one might be, explain why the use of a normal distribution is appropriate. And quite often, it's a case of explaining either this or this. When you've got a situation where you've got the mode, median and mean are the same, or when you're perhaps doing a box plot question and you've been asked to do this calculation, see if there's any skew. If there's no skew, then that's normally the case for a normal distribution. But that's not all. That's not all, because so far I've been talking about discrete random variables, okay? Now, hold on, I'm going to show you what continuous random variables look like in a minute. I've just got to tidy up my board. Okay, took a little while to draw out, okay, but I wanted to illustrate an example of what a continuous random variable looks like. Now remember, we're only talking about symmetrical distributions from now on. Now you might be able to see, particularly if you zoom in, that I've got gaps in between these bars, but I've got no gaps in between these bars, okay? But why have I drawn them so small, short together, okay? Well, when you've got continuous data, often they are grouped. You're talking about group data. A very typical one is height. So this could be the heights of either males or females, or the whole population for that matter. Okay. However, the smaller the groups that we're dealing with, the better, because we can actually analyse the data a lot more, particularly these days with the technology that we've got. Ideally, we'd want to have a continuous set of data without any groups. A continuous set of data without any groups. Group data is fine, and let's be honest, when we're dealing with simple statistical calculations like you might have done at GCSE or even up till now, when you're dealing with group data, it's quite easy to find the mean or to find the median or use interpolation or something like that, isn't it? But ideally, you don't want to group the data at all, you want to just list them all. And with Excel spreadsheets and so on, it's quite easy just to list all of the data. Now, what happens when you plot the graph when the data is just listed and it's not grouped at all? Well, if you don't have groups, of course, you don't have bars, because the bars are there to represent the different groupings. If you just plot the data as it's listed, you don't have bars, you have some sort of curve. And the curve will look something a little bit like this. I'm sorry I'm using the same colour, but it's kind of easier if I do so. So what I'm doing is I'm trying to draw a curve through the tops of the bars there. I've not done an exceptionally good job of it, but you get some sort of curve. Now, a screenshot will be handy here, so I'm going to insert one. Here we go. So this is a screenshot showing you ungrouped data for the heights of females and the heights of males. And notice that for both of them, you've got this lovely looking curved shape. For each set of data, for the males and the females, it is symmetrically distributed. Now, these are what we call a normal curve, okay? Right, back to my board again then. So this is what we call a normal curve, okay? Yes, we've got there a normal curve. That's what it's all about, okay? So it's for continuous data, okay? And the curve is perfectly symmetrical about this point here. And on our horizontal scale, that point is the mean, which we often call mu. Remember, the mode, median and mean, they're all the same, okay? But it's important to recognise that the normal curve that is drawn for any particular set of data, when it's symmetrical, of course, the mean is the central point there, and that's very important, okay? So we're looking at continuous data, and the mean is that point there, okay? Now, normal distributions help us to calculate probabilities. So before I say goodbye to my discrete diagram, because we're not talking about discrete data, let me just illustrate a point to you about probability. With probability, with discrete data, we're often looking at the probability that x takes a particular value, aren't we? So for example, we might be looking at the probability that x is, let's just say 5. And on an example of rolling dice, we could work out the probability to get 5 on a particular set of roll of dice. Okay, you get 2 and 3, 3 and 2, and so on. Okay, or we can work out the probability of x is equal to 10, or depending on what the data distribution is, x is a particular number. But in any case, we're looking at this, aren't we, with discrete random variables. The probability that x takes a particular value. With continuous data, if you look at the same sort of thing, if you're looking at the probability that x takes a particular value, it doesn't matter what it is, 2, 3, 5.5, pi. Remember, this is continuous data now, so you can have any real value. Okay. What you're doing is essentially you're looking at this particular value there, where that might be x, and you're working out the probability of that. Now, with the bars, okay, there's a visible thickness to each bar, isn't there? Okay, and you can work out the precise probability of it. For example, the probability of rolling 7 with 2 dice, you get 1/6. Okay, but when you've got continuous data, the probability of that particular bar is effectively so small you can consider it to be 0. Why is that? Why is that? Well, let's just suppose these are heights of people, and the heights range from, I don't know, 130 centimetres to, let's say, 180 centimetres. That sounds reasonable, doesn't it? Okay. Find the probability that someone has got a height of, let's just make up a number, 143.2756892376598 centimetres. There you go. For my simple example, can you see why the probability is going to be extremely small? Let's just choose another one. Any number between 130 and 180. Find the probability that someone has a height of 163.2789432605327986532565325 4, 3, 2, 0, and etc. I think you've got the point, okay? It's extremely small, okay? Just as the probability of getting someone with a height of exactly 130 centimetres is going to be equally small. So what I'm saying is, in this continuous scale, where you can fit an infinite number of different heights, think about that, because it's continuous data, you can put in any number you want in there, any rational or irrational number between 130, 180, you've got an infinite number of choices to make, yeah? An infinite number of choices to make. Now you're trying to find the probability of just one of those infinite choices happening. Can you see why? The answer is so small, we effectively call it 0, okay? So the probability of this happening is actually 0. So when we're looking at a normal curve, we don't look at probabilities of x taking a particular value. We look at the probability of x taking a range of values. We look at probability of x taking a range of values. What's the probability that the height is between, say, 140 and 150 centimetres inclusive, or something like that? Because then, if we took, say, a range of values, that gives us an area underneath the curve, and we can actually calculate what that is. Effectively looking at the proportion of this curve of heights that will be in a particular interval. I'm really hoping that makes sense to you, because the important part about the normal distribution in the unit we're looking at is we are considering the area under a curve to give us a probability of something happening. I'm hoping that made sense. Okay. If it didn't, either play the video again or just remember this. We're looking at area under a curve. Yeah? Yeah. Right, next is a screenshot, a very helpful screenshot, I'm hoping. Here it is. Right, so here's my screenshot of a normal distribution curve, okay? Now notice the shadings and the percentages. I'm going to talk about that in a minute. The reason for this is because, as I've just said, we are looking at the proportional area underneath different parts of the curve, okay? The proportional area underneath different parts of the curve. Right, let's just talk about what these shadings actually represent. Right, let's talk about some properties of the normal curve, shall we? Sometimes called the Gaussian curve after Carl Friedrich Gauss, sometimes called a bell-shaped curve. But whatever, I call it a normal curve, okay? So remember, it's got a symmetrical property about mu, the mean, and we need to talk about standard deviations here as well. But before I do, let me just point out that everything underneath the normal curve includes the entire global population. That is the entire population of whatever it is you're studying. So if you're studying the heights of everybody in a school, everything under that normal curve covers all the heights in the school, okay? And what's important to realise is because we're looking at probabilities, we're looking at probabilities of a height, in this case being a particular value in a range, so either between 130 and 150 or 150 and 160 and so on. We're looking at area underneath the graph, and since all probabilities add up to 1, then we can say the entire area under the curve is 1. That's an important characteristic of the normal curve, okay? The entire area under the normal curve is actually 1. Now, for those eagle-eyed of you, or for those who've zoomed in to see, you'll notice that my curve does not actually make contact with the horizontal scale. That is done for a reason, okay? That is done for a reason. It's because the actual curve is asymptotic. What that means is that the horizontal scale is an asymptote, yes, in both directions. So in other words, as this scale tends towards infinity, I'm trying not to call it the x-axis, notice, okay, because it's not the x-axis, it's just a horizontal scale. It could be height, it could be weight, it could be something else. But as this scale tends towards infinity, yes, the actual graph of the curve will tend towards 0, but it won't actually be 0, okay? And the same with this as well. Don't have to worry about that for the moment. That's more mathematics, okay? This is more statistics, and yes, I am separating the two branches there, okay? Some might argue this is mathematics, yes, but this particular branch is statistics. When I say this is mathematics, I'm getting into, sorry, I'm going off on a complete tangent there, all right? It's calculus mainly, all right? I've got another video about that somewhere, actually, okay? For those of you interested, the video you want to look at, if you all want to look, this is the video where I talk about how to integrate e to the negative x squared dx. Okay, so if you want to have a look at that now, then just go. But I just do want to forewarn you, it's a heavy going video. It takes 30 minutes, which is why I'm not going to talk about it here. Okay, I'm going to just get rid of that for the moment. Right. Anyway, back to this. So what's the important thing here is curve, symmetrical, mean in the middle, and we're looking at the total area equal to 1. And now let's talk about standard deviations. So this point I've marked off as being one standard deviation above the mean. Remember, standard deviation is how spread data are from the mean. Okay, so on a particular set of data, one standard deviation above, two standard deviations above, three standard deviations above. And because of the symmetrical nature, one below, two below, three below. Now it's important you recognise what percentages make up this population of data. Now approximately 68.3, that's an approximation, some say 68, okay, but approximately 68.3% of data lie within one standard deviation of the mean. That's particularly important, okay, so one standard deviation within the mean. So a fair amount of data, just over 2/3 of course. However, quite a significant percentage of the proportion lie within two standard deviations of the mean. 95.4%, some say 95% approximately, of all data lie within two standard deviations of the mean. Let me just shade that in for you. So if this is two standard deviations above and below, what we're saying is all of this part of the graph here, all of that data represents 95.4%, which is most of the data. That is really important. Why is that really important? Because when we're looking at statistical analysis, we want to consider as much of the data as possible. We want to consider as much of the population as possible. And 95.4% is the majority of data. Now, even greater set of data lie within three standard deviations of the mean. So 99.7% lie within three standard deviations of the mean. It's wrong to say 99% because obviously because of the rounding. It's equally wrong to say 100%. Okay, because we're not looking at 100% of the data. Obviously you have extreme values. You've got outliers, both large and small, in a wide variety of cases. Sometimes all of the data will be within three standard deviations of the mean. Okay, sometimes it happens. For example, when you're looking at, I don't know, the heights in a very small class, okay, people, okay? If everyone's between, say, 140 centimetres and 150 centimetres, because in the same year group, you're not going to get anyone that is standing out, okay? These are more appropriate when you've got a larger set of data, okay? I'm rambling on a little bit, but I feel like in statistics, sometimes a lot of things need additional explanation for you to help with your understanding. All you need to be aware of is that most of the data, not all, but most, the vast majority of data, 99.7%, lie within three standard deviations of the mean. That means if you're three standard deviations above the mean or below the mean, you are exceptional. For whatever reason, okay, you are exceptional. You're an outlier, and it's down to your interpretation there as to what exceptional actually means, okay? Now here's a graphic for you, a slightly better version of the diagram that I've drawn. Here it is. So here we have our normal curve, and notice with the shadings again, you've got the, well, you can add it up, you've got 68.3% either side of the mean, and then of course you've got approximately 95% and over 99% of the data lie within three standard deviations of the mean. Now look at the integral on the top right, you can see that? That is very similar to the integral that I wrote down, okay? It's important you recognise that. You don't need to know or worry about integration in this unit. Do not worry, okay? You don't even need to have to worry about the integral of that in A-level maths, okay? Because it is probably something that you'll see if you go to university to study maths, okay? But if you are at all interested in that integral, let me just sum up for you, okay? The entire area of the curve is equal to 1, so in other words, your solution to that integral between limits of negative and positive infinity will be 1 as well. If you want an explanation, I refer you back to my YouTube video that I mentioned. You look up the integral of e to the negative x squared, okay? Okay, I just want to round off this presentation by giving you some important notation. Okay, so in terms of our normal distribution, it is quite often to see this. And what does that actually mean? It's shorthand for saying that x is a normally distributed random variable. So it's x and then wavy line, normally distributed, because there are other distributions as well, such as a Poisson distribution, which you may or may not see. Okay, there's also a binomial distribution. You might have seen a binomial distribution in pure maths, but we use a binomial distribution with probability work. But in this case, when it's a normal distribution, we have this x and then wavy line capital N. That means that x is a normally distributed random variable. And then in brackets, that's important, okay? You're normally given two numbers, okay? Usually given two numbers. The first is the mean, mu, and the second one is the variance. A little bit awkward because obviously the standard deviation is what we'd rather have for the graphical purposes, okay? But since the standard deviation is sigma, then that's labelled as sigma squared. So it's quite often for you to see something written like this. Let me just show you an example, okay? So it might be that in a particular question, you are given this. X is normally distributed, and then 8, and then 0.2 squared, okay? Yes, I have just gone for an example in a textbook right in front of me, okay, because it was there and it was simple to use, all right? Sometimes it is given as the actual number, in which case you've got to square root it, okay? But sometimes it helps you out and it tells you 0.2 squared. So from that, what you can infer is that the mean is going to be 8 and that the standard deviation is going to be 0.2. So if you were to draw a graph with a normal curve, this is what it would look like. You could label that mean point as being 8 and then one standard deviation above, so 8.2, and then two standard deviations above, 8.4, and then three standard deviations above, 8.6. And then the other way, one standard deviation below, two below, and three below. Okay, so that is what your normal curve actually looks like. Incidentally, don't worry about the heights. You probably won't ever have to label what the height actually is. Okay, it's not an important part of the question. Why is it not an important part of the question? Well, to be honest, the height axis might not as well be there. Okay, you could just rub it off if you want. If you want to label something, label it as probability density. But we don't need to talk about that because what we're interested in is using this information to help us with probabilities. Let's just consider a couple of simple probabilities, okay? Let's just consider, let me just rub this off. Let's just consider calculating the probability that, and it's x is equal to 8. I'm trying to catch you out. It is 0, isn't it? Remember what I said earlier? Rewind again if you can remember. But the probability of x being a particular value is 0. I'm not going to say the explanation again. Okay, but what I will highlight is that often you're asked to work out things like this. Probability of x is greater than 8. Okay, so what does that mean? Well, it means that you're looking at all of this part of the graph, isn't it? I don't want to shade it in because I'm going to use the graph again in a minute. Okay, but you're looking at this part of the graph. What's the probability of having a value that is greater than 8? It's a half. Okay, it's a half. We often use decimals, has to be said, in this sort of work. Again, you'll see why later on, but you know, let's just get one thing straight away sorted out. We use decimals with this sort of work, okay? Because it's exactly half of the graph. Now, what if I ask you this probability? Probability of x is greater than or equal to 8. It's the same, isn't it? 0.5. Why is it the same? Because the probability of x being 8 itself is 0. So don't worry about the inequality symbols for the time being, okay? Don't worry about that, it's exactly the same. What if I asked you to work out the probability that x was greater than, say, 8.2? Okay, I'm choosing an easy value. Okay, so 8.2 is there, isn't it? Okay, let's just put it in. Now, in terms of shading, I'm after you to work out that bit there. Okay, now what you need to know and use, so I've just noted them here because I can't remember the exact values of these to one decimal place, if I'm honest. Okay, you're looking at this being 3 standard deviations within the mean, this being 2 standard deviations in the mean, this being 1 standard deviation within the mean. Now that is 1 standard deviation, isn't it? Okay, that is 1 standard deviation. So what you want to work out is what the entire area of that bit there is. Okay, that's what we're after. So I got to the end, then I realised my video stopped recording somewhere, so I'm going to try and pick it up. Okay, so I was talking about this, wasn't I really? I was talking about what's the probability that x is greater than 8.2. What's the shaded region you want? So let me just indicate it's actually everything, okay, above 8.2. Well look, because we're talking about 1 standard deviation above Yeah, we're talking about one standard deviation above. What that means is that this bit here, let me just put an arrow to it, that's got to be 34%, okay? So I'm using these, but I'm going to round it to 2 decimal places in probability terms. So 68.3% would be 0.683. So I'm talking about 34% being between there and there, okay? So half of that is going to be 0.34. I'm hoping that made sense to you. Okay, let me just say it again. Because within one standard deviation, that bit there is 68%, 0.68. That bit there, which is half of it, is 0.34. Hoping that made sense. So that bit is 0.34. Okay. All of this side here, that represents half of the data. That's 0.5. So you can see what I'm doing here. So what that means is all of this up to that point there in total has got to be that plus that, which is 0.84. Okay, so all of that is 0.84. So what that means is because the entire probability adds up to 1, we can calculate this bit here must be the difference between that and 1. So 0.16. Okay, and what I've given you is an example of how we often use the curve to work out probabilities. We often look at the probability of everything up to a particular point and then consider what is left. Okay, that will become very important a little bit later on. I'm hoping that was helpful to you. Let me give you another one. Okay, this time I'm going to give you a probability that x is in a range of values. Right? So what's the probability that x lies between, let me give you a simple one, 7.6 and 8.4. Whoa, I missed off the inequality sign there. I beg your pardon. Let's try it again. There we go. I was too focused on the actual number I was going to use. Okay, so work out that probability there. Now again, the diagram, let's see what that is. That's between here and here, isn't it? And the reason I made it nice and simple for you is because that is 2 standard deviations below the mean, and that is 2 standard deviations above the mean. Okay, so it's actually quite easy to work out. Again, you'll look at your actual percentages there. So 95.4% of data lie within 2 standard deviations of the mean. This is 2 standard deviations of the mean, so as a decimal, I'm going to round that to 0.95. Okay, quite often at this level, at the moment, early stages, 2 decimal places is enough. Okay, so there's some simple probabilities there for you. Okay, I'm hoping that made sense to you. I'm hoping you know a little bit more about normal distribution now than when you first began the video. Okay, well, I wish you a good day, and I'll see you again. Bye bye.